Yeah, thank you very much. I'm very happy about the opportunity to have been participating in this competition, and I'm even more happy about the prize. So it has been a great experience being here. I will tell a few words about that in a minute. I have worked with APL before, but it's great how much I learned here and how much I got some insight into where Dyalog APL is growing. That's it was and still is a great experience. So at first, maybe I should apologize a little bit about the slides. I usually do my slides in LaTeX and a Beamer class, but I noted too late that it doesn't work with Unicode output. So tried to get XeTeX working, but it didn't work out. So what I wanted to say is I think the world would be a very great place for APLers if everyone just supported Unicode. Okay, so but on a more serious note, this thingy is not working. Oh, it is if I pointed it the right way. Yeah. So who am I? So I'm somehow new to the APL community, but I'm not really new to APL. So I've professionally worked with APL for 6 years now. By the way, I tried to spell my name using APL symbols. I'm not very happy about my surname, so if anyone wants to propose something different for B and for K, I would be very happy to hear about it. But still, so how did I get into contact with APL? So my academic background is in mathematical logic, and I did a little bit of programming or problem solving there. Not in APL, but mostly in Haskell. So that's where my point of view comes from. So I have a background mostly in functional programming, not so much in more classical programming paradigms like procedural or object-oriented. But after I left academia in 2017, I was searching for a job in industry. And I thought it would be nice to do something with mathematics because I'm a mathematician. And so I got into the insurance industry. So I applied to this big German life insurance company. And in the job description, there was something like, oh, a candidate should be able to program. And I thought, okay, that's a bit vague. So I went to the job interview and asked them, so what are you using here? What kind of programming language? Is it Java or is it Python or what? And they said it's APL, and maybe they saw the question marks in my face, and they said something about, yeah, APL is an abbreviation. It stands for a programming language. And I thought, oh, that's pretentious, but oh, okay. I will look into it. So in the evening after the job interviews, it was a 2-round interview, and that was the first round. I went and I looked into Wikipedia, and I looked at the syntax and thought, wait, that's strange, but it's also nice, actually. So I tried to learn a little bit of APL for the second interview, and I got the job in the end, and had the opportunity to work there with Dyalog APL. So I wasn't a full-time APL programmer or developer. I'm more like a domain expert actuary who used APL to solve problems. So later on, in 2020, I changed my employer and went to another big insurance company where I work now, Viridium Group, or more precisely Proxalto, which was former Generali Life Germany, but yeah, that's probably not too interesting. Anyway, I moved from Dyalog APL to APL2, which is just still a thing in Germany for some reason. That has something to do with IBM mainframes or something like that, I guess. But it was an interesting experience, working with a team of many people in APL2. So I'm back to Dyalog APL now. So we migrated the year before last year, and I'm very, very happy about that. And I'm also very happy so I'm one of the people I think Morten talked about in the very beginning, one of the new APLers. So I learned APL in this millennium, as you can see. So, and still have to write the big next application, but still. So I'm really looking into this opportunity to use modern modern ways of development in big teams, because it's really hard to do if you don't have stuff like version control and stuff like that. So, and Dyalog APL does have this, and Dyalog APL also, as far as I have seen now from the presentations and the workshops, it's in my opinion, it's going in a nice direction with respect to tooling and planned tooling. So that's my APL journey, essentially. Just to say how I got into contact with APL, because I mean that's part of how I got won the APL competition. Of course, I had to learn about APL before. But before I bore you too much, I should go into the problems. So I will present my solution to two problems. One from phase one, which is I think a bit unconventional, and one from phase two. So the phase one is just to highlight what I like about APL, essentially. And the phase two was one that I personally struggled most with, so that I found the most difficult problem. My solutions are on my GitHub, so if anyone is interested in seeing it, please don't look too closely at the problem with the money to make change, because I found out when presenting this, so preparing this presentation, that I made a mistake there. So it's a corner case that doesn't work. Funnily enough, it doesn't work, I think, with Danish currency, because it doesn't have a one denomination. Anyway, so as I said before, I'm an actuary. I'm actually a certified actuary. So by law and custom, I'm obliged to talk about risk whenever I have the chance. So I will do that now. I will present my solution to the problem risky business, which was one of the phase one problems. Of course, it's not really about risk. It's about the board game Risk, which many people might know. So if you don't know it, it's a game of world conquest, which is maybe not a nice thing, but let's look at it abstractly. It's a two players, or multiple player game, and players can invade countries of other players, and if they do that, they have some units, and there's an attacker and a defender. An attacker usually has up to 3 units, and a defender has up to 2 units, and they just throw dice, essentially, against each other. And then the dice are compared. So they are sorted in descending order, like here. And these dice are then compared. And if there's a tie, the defender wins, so the attacker has more dice, but on a tie the defender wins. And on the other hand, if the value of the attacker is higher, then the attacker wins, and winning means the other player essentially losing a unit. Okay? And the problem was writing a function which, given a descending list of dice results for the attacker and for the defender, so for the attacker on the left, for the defender on the right, give a vector with in the first, so the first number is the amount of units that the defender is losing. The second number is the amount of units the attacker is losing. Okay, so that's exactly the example from the other slide. Of course, I mean, there is no reason to just stick to realistic outcomes, right? I mean, we can just generalize it to an arbitrary length, right? We don't have to have length 3 and length 2. And I should point it in the right direction. We should also make it in a way that handles also if we only have one die at on every side, but we still expect the input to be vectors and not scalars. And also we don't really have to restrict ourselves to 6-sided dice ranges, right? I mean, you can just compare arbitrary integers. So how did I solve it? So of course, it's a phase one problem, so I had to put in a one-line solution, but I just took a 3-line solution and diamondized it, but I don't have to do that for this presentation, I guess. So that's not my solution yet, but I think it's easy way to just show what the idea is, right? I mean, what we do is, as you saw in the first picture, if there are any additional, if there are any additional dice In the longer sequence, we just ignore them, right? So before we compare, we should make sure that both sides have the same length, namely the shorter length, right? So I calculate the length first, and yeah, what is this? I just said it, it's the minimum of the two lengths, right? Then I shorten both. Yeah, I assume that the input is already in descending order, so I won't order it. And yeah, the result is then just, in my description I switched the order. So the first element is actually what the attacker lost, and the second is what the defender lost. Okay, that's nice, but it's also too long, I guess, right? I mean, this is wasteful, right? So if we think about tacit functions and stuff like that, and I'm really a friend of, as I said, I came from Haskell, I'm a friend of point-free programming. Let's do it this way, right? I mean, over is really nice. We can just not only save a symbol, well, maybe we didn't really save a symbol, I didn't count, but yeah, I think it's a really nice way to say we do the same thing to both sides, and then we apply another function. And I think that's a really great thing about APL, because this is something that you really do a lot. And that's essentially my solution. But I think, looking at it now, I didn't go far enough, because you can also do it here, right? I mean, you're doing essentially the same here, right? But you need to curry, right? But then you can do that. So that's what I would send in if I would send in the solution today, but I didn't. So that's the reason for this disclaimer. Okay, so that was the phase 1 problem. Now we get to the phase 2 problem, which I said was, to me at least, the most difficult one. So I think I was one of the people who really sent in their full solution quite late, because I got to know about this Dyalog competition, and I started to work on it, and I worked on it, I think, 2 evenings long, and then I solved most of the problem, except for this last one. And happily, there was a holiday around the time that the competition ended, and so I had the opportunity to get back to this problem and solve it, and after that send in the complete solution. Okay, and this problem is array partitioning. Okay, so I think it's a slight misnomer, because we don't really partition in the sense of taking an array and splitting it up into disjoint parts. But I will just, yeah, I will explain what exactly the problem is. So the goal is to write a function partition, right, which takes an array to be partitioned in a sense, and a specification of the partitioning. And the specification in general will contain 3 parts: a shape, yeah, so the result will be a vector of parts of the array here, of a certain shape. We also give a movement size, right? We are running along the array and splitting it. I will show you an example on the next slide. And the first, where we start to partition, essentially. Okay, what I want to show you in this slide is, that's a slight difficulty, the movement and first parameters are optional. And to make it a little bit more difficult, the spec itself may be of depth 0 or 1. Right? So if we only supply a shape, it can be in scalar form, it can be a vector. So we have to, it can even be a vector of length 3, right? So we have to make sure that we don't intermix our input. Okay, so, but what does it do? I will show it, because of time constraints, I will show it with some examples. Okay, so that's an easy example, right? We start with iota 10, and we want to partition this iota 10 with a shape of 3. What we do is we start in the beginning, take the first 3 elements, that's our first element, then we take the next 3, the next 3, the next 3, and so on, until there's nothing else that would fit the bill in the sense of the shape we are looking for. Right? I mean, that's the easiest case, essentially. Okay, so let's see what happens if we take all the parameters. As I said, this is the shape we want to get, this is the movement, and this is the first, right? In this case, because we have just iota 10, we start essentially here, right, at the 4th element, take the next 3 elements that are the first thing that we have. Thank you. We have a movement size here. That means we don't take the next one. So we don't take 5, 6, 7 next, but we take 6, 7, 8 because we move 2 to the right. After that, we again move 2 to the right. Okay. We're supposed to be able to do the same for higher rank, right? So I won't really go through that, but yeah, even if we take a matrix and or 3-dimensional tensor or something like this, it should still work, of course. We must assume that we put something sensible as left parameters. Okay, but a very interesting edge case, which gave me some bad sleeps, was what happens if we want to partition a structure which is not big enough to be partitioned, right? Like in this case. So we do a 7 partition iota 6. I mean, there are no 7 elements. So something that we could do, we could fill it up with some prototype type element or something like this. But that's not what we do. What we do is we get back an empty vector. Okay, this part is easy. The next part is also easy, but you have to think about it. This vector should have a prototype fitting the shape that you requested, right? So it's not only an empty vector, but we also have, in this case, a prototype that matches. So in the element, essentially, that is not there, we need a prototype that matches a length 7, which we requested, right? Okay. So how do we do that? Part 1 is taking care of this funny business here, which is possibly not the most interesting part, but yeah, you really have to take care of that. So what I did first is I'm missing the word. I want to say enclose, but that's not the right word. Sorry? Nest. Thank you. I was really looking at this word. I was saying, I have to take care of remembering it, but when I really need it, I forgot it. Okay, yeah. I nested in order to make sure that I really have a structure that I can work with. If I already have this 3 vector or 2 vector that is a standard specification, nothing happens. But if I get a scalar or something especially if I get a scalar, I want to have a vector here. Okay, so I have to supply some defaults for movement and for first, right? I mean, they are just the obvious things to do. My standard movement is, of course, a step size of 1. My standard start is coordinate 1, but it has to be of the right shape, of course. From this, I calculate my shape, movement, and first. By just taking my specification, which might be incomplete, reversing it, prepending my defaults, and taking the last 3 elements and prepending it again. I don't know if that's the most efficient way to do it, but it makes sure that in the end I have a triple, which contains information that was supplied as a left argument if it's there, and it's filled up with a default if it's not there. Okay, that's what happened here. By the way, if you should look at my solutions on GitHub, which probably not many people will do, but still, you might notice that I have shortened some names here because I personally am a friend of long names, which is, I think, not the APL way, TM, but when showing this, I call that default and not def. So anyway, so we will skip over the next part because of time. So what about the first parameter? So I want to start my partition at some point, which was supplied by the first. By the problem statement, we don't have a negative movement, right? So we only move positively, right? So we can just take care of all this stuff by dropping everything that comes before first, right? It's just reducing a problem to another problem, right? Afterwards, I can just ignore what happens with first. And that's exactly what I do here, right? I make sure that my array is truncated in such a way that I don't have to take care about the first parameter anymore. It's just the array, and our new start is what was first of the original array. Okay, and then we have to handle the edge case, which in the end turned out to be not too hard. The edge case that we take too much in our partition is exactly the case where we have one component of the shape of the supplied array being strictly smaller than an element of the shape, which we supplied as a parameter. Right? And if we do that, we just pack it up and put out an empty vector, and we'll automatically have the right prototype. Okay, so this might be a bit disappointing for people, because I heard this problem described as a problem to, in some way simulate stencil. Yeah? But as I said in the beginning, I'm a friend of modern workflows, and I'm also very excited about the stuff with Cider and Taton, what is happening. So I'm really happy to use stuff that other people supply to me, like, for example, built-in primitives, like stencil. So I'm too lazy to implement it myself. I just use lazy, actually. I use stencil. I don't use lazy. Because time is short and I won't have time to explain stencil in all detail, I will explain stencil in the special case that I apply this function to the left. If you don't know stencil, just don't think about it. And what does it do? Essentially, it's a sliding window over a structure. Yeah, I supply a shape here, I supply a vector here, and in this case, what happens is I have a sliding window of vectors of length 3 that just goes over my structure, and by this, I build up the result. Right? It has a movement of 1. And it's this funny business that it might overtake, right? I mean, it might take more. It might hang over. No, it overhangs essentially, right? I mean, it goes out of the vector, because the point of our stencil is that it's somehow centered, right? So if we have this case where we have a vector of length 10, and 10 is not divisible by 3, obviously, we have to make sure that we do something symmetric, and the symmetric means in this case that we have a 1, 2 at the beginning and a 9, 10 at the end, although it doesn't have a shape of 3. We can do something very similar when we have higher ranks, right? I have a shape of 3, 4, and I have a shape of 3, 3, and I supply a 3, 4 row iota 12, which is this one. Okay. That's everything that we need to know about stencil in order to solve this problem. Okay, and that's what I do, right? I use it. I take this partition with overhang, there's a long name, by doing exactly what I just showed you in more general, yeah? I mean, I have my shape here, I have my array here, everything is fine. But I have this overhang, which is not right? I mean, if we look at now this animation is catching up to me. Yeah, if we look at what happens with a shape of 3 and a iota 10, we are nearly at the right solution, but we have to take care to delete this and delete this. But that's easy, because the ones that have the elements that overhang are just the ones where the shape's not what we expect. I mean, it's a brute force solution. Maybe it's not the best one, but it works. Okay, and I can collect the indices of all these elements, which don't overhang. Okay, but now I have to take care. So I did take care of the partition. I did take care of the first. I didn't take care of movement yet. Okay, that's the part that is still missing, and that's the last part actually, and then I'm done. First, okay, some bookkeeping. So I take an index where I start, essentially, and then I want to move. But what does movement mean? Of course, I want to take the indices from the start, which are generated by adding an integer multiple of the movement vector to the start index. That's essentially what I do here, right? I take all my full indices where I don't have overhang, right, and look at those ones which where the difference between between the index and the start vector is divisible, is evenly divisible by the movement. Okay? And then I just keep them. So I select them, and I'm done. That's it. Okay. So I see some people wondering. I have 2 minutes. That's great. But I'm done, actually. So I want to thank you. Now you can clap.